Welcome to Analytical Chemistry Vision, a platform dedicated to exploring the theoretical and experimental aspects of chemistry, blending classroom learning with laboratory research to enhance understanding and inspire innovation in chemical science. Let's begin an interesting and highly useful topic for UG, PG, and research students: precipitation and complexometric titration. These techniques play a vital role in determining water hardness and chloride content in drinking and environmental water samples, ensuring quality, safety, and accurate chemical analysis. If you've not seen part 1 and 2, please see where you learn about primary standard and secondary substances, equivalent and molecular weight, expression of concentration of solution, internal and external indicators, acid-base and redox titration and indicator theory to explain the color change of indicator used in titration. In this part, we will learn what is precipitation titration. Precipitation titration is based on the formation of an insoluble precipitate between titrant and analyte. The endpoint is identified using a suitable indicator. Example: in Mohs method, silver nitrate, AgNO3, reacts with sodium chloride, NaCl, to form white AgCl precipitate. Potassium chromate, K2Cr4, acts as an indicator, producing a red-brown silver chromate, Ag2Cr. O4 color at the endpoint, showing the completion of the titration. Here we will learn the adsorption indicator theory or Fudgens method to explain the color change of indicator at the endpoint. Fudgens method is based on the adsorption of ions from the solution onto the surface of the precipitate formed during a titration. The indicator changes color due to a change in the surface charge of the precipitate as the reaction reaches the endpoint. Mechanism: first, at the beginning, Cl minus ion are in excess. All Ag plus ion from AgNO3 reacts first with Cl minus ion to form AgCl, white, as shown in the image. Second step is, as titration proceeds, chloride minus ion get consumed and just at the equivalence point, a tiny excess of silver plus remains unreacted. Thirdly, these excess Ag plus ion react with chromate ions, Cr. O42 minus from K2CrO4 to form Ag2. CrO4, which gives a distinct red-brown color marking the endpoint. Here we will see solutions needed for precipitation titration. First one is 0.005 gram AgNO3. Normal is prepared by dissolving 0.085 gram substance dissolved in 100 ml of distilled water. Second, 0.005 normal NaCl is prepared by dissolving 0.029 gram of NaCl in 100 ml distilled water. Third one is 5% K2Cr2O4 solution. For this 0.5 gram of substance dissolved in 10 ml of DDW. See here, the methodology for precipitation titration by Mohs method. Take 10 ml of NaCl solution into a clean conical flask. Add 0.5 ml potassium chromate indicator. Titrate against 0.005 molar silver nitrate solution taken in the burette. Stir continuously during titration. The endpoint is the appearance of a permanent reddish-brown color due to formation of silver chromate, Ag2Cr. O4 complex. Note the burette reading and repeat for concordant values. Calculate the concentration of silver nitrate by using N1 and V1 equal to N2V2 formula. Precipitation titration is a simple and reliable method for determining chloride ions in real water samples such as river, pond, drinking water, industrial effluents, rainwater, and tap water. In this method, chloride reacts with standard silver nitrate to form a white precipitate of silver chloride, and the endpoint is detected using indicators like potassium chromate or adsorption indicators. This technique is highly important for UG, PG, and research students, as chloride levels directly reflect water quality, pollution sources, and industrial contamination. It is widely used in environmental monitoring, drinking water safety assessment, and dissertation or project work to provide accurate chemical analysis essential for public health and environmental protection. Here we will learn how this precipitation titration be used for quantitative determination of chloride in river, pond, drinking, industrial waste, rain and tap water sample. Formula is, chloride in is equal to V1 minus V2 into M into 35.46 into 1000 divided by Vs, where V1 is volume of AgNO3 for sample titration. V2 is volume of AgNO3 for blank titration. M is molarity of AgNO3. Vs is volume of water sample taken for titration. This table showing the determination of chloride in river, pond, industrial waste, rain, tap, and well water samples. For this 6 each samples were collected in polyethylene bottles from this region and analyzed using precipitation titration. The concentration of range of chloride in river water was 22.6 to 55 mg per liter, pond water was 45.6 to 89.7 mg per liter, industrial waste was 150 to 350 mg per liter, rain water was 4.8 to 8.1 mg per liter, tap water was 18.6 to 55.2 mg per liter, and well water was 22.7 to 66.6 mg per liter. The results indicate that chloride levels vary widely across water sources, with industrial waste showing the highest contamination. River, pond, tap, and well waters fall within moderate ranges, while rainwater shows the lowest values, reflecting minimal atmospheric chloride pollution. Finally, we will see here fourth type titration. Complexometric titration. Complexometric titration is a volumetric analysis technique used to determine the concentration of metal ions such as Ca2+, Mg2+, Cu2+, Zn2+, etc. in solution. It involves the formation of stable, water-soluble metal ligand complexes at pH 10 using chelating agents such as ethylenediamine tetracetic acid, EDTA. Indicators like areochrome black T, EBT, are used to detect the endpoint through a characteristic color change from pink to blue. Here, the question is, why the color of the solution changed from pink to blue? At the endpoint of complexometric titration performed between EDTA and metal icons using areochrome black T as an indicator. The change from pink to blue can be explained by metal indicator theory. As we know that, in complexometric titration, metal indicators are special dyes that form weakly colored complexes with metal icons. This can be understood by different steps. In first is, at the start of chemical reaction, Ca2 plus ion in sample bind with EBT, forming a pink colored complex at pH 10. Next, the second step is during titration, EDTA is added. EDTA has much stronger affinity for cover than the indicator. EDTA forms stable Ca2 plus ion form and free the indicator in aqueous solution showing blue in color. When all Ca2 plus ion are bound to EDTA, the indicator becomes free, uncomplexed, and its color changes back to blue. Here, we will see the solution preparation. First one is, 0.01 molar solution of disodium EDTA is prepared by dissolving 0.372 gram of substance dissolved in 100 ml of double distilled water. Second one is, 0.01 molar zinc sulfate is prepared by dissolving 0.197 gram of substance is dissolved in 100 ml distilled water. Third one is, 10 pH buffer solution, which is prepared by taking 0.46 gram ammonium chloride and 3.8 ml of ammonia and then diluted to 10 ml distilled water. Fourth one is 0.5% EBT indicator, which is prepared in dissolving 0.05 gram of substance 10 ml ethanol. Here, we will see the methodology for complexometric titration. First, take 10 ml of ZnSO4 solution for standardization, and further 10 ml of sample, tap, pond, river, are taken into a conical flask for hardness determination. Second, add 1 ml of 10 pH buffer solution. Third, add 2 to 3 drops of EBT indicator. The solution will be wine red if calcium or magnesium present, indicator metal complex. Fourth, titrate with standard sodium EDTA solution from the burette while swirling. Add EDTA dropwise near endpoint. Fifth, endpoint, color changes from wine red to pure blue. Record volume of EDTA used. Next, N1V1 equal to N2V2 is used for concentration determination of EDTA. Let us understand how we can apply this complexometric titration in determination of hardness in terms of calcium carbonate in drinking water or other water samples, using following formula. Total hardness in will be equal to V1 minus V2 into M into 100 into 1000, and whole divided by Vs where V1 is equal to volume of EDTA for sample titration. V2 is equal to volume of EDTA for blank titration. M is molarity of EDTA, Vs is volume of water sample taken for titration. Hardness analysis in drinking and tap water is important for health because calcium and magnesium support strong bones and metabolic functions. However, very high hardness may cause digestive discomfort, while low hardness increases corrosion risks. Monitoring ensures safe mineral levels and protects long-term health. Similarly, we can use EDTA complexometric titration for analysis of hardness in river, pond, industrial waste, rain and tap water sample. Because it accurately measures calcium and magnesium levels, detects pollution or mineral load, supports water treatment decisions, protects public health, and ensures water quality for domestic and environmental use. Here, different river, pond, industrial waste, rain, tap, and well water were collected in polyethylene bottles from this region and analyzed using complexometric titration. The concentration of range of hardness in terms of calcium carbonate in river water was 82 to 190, pond water was 85 to 205 mg, L, industrial waste water was 325 to 750, rain water was 5 to 10 mg, L, tap water was 80 to 150, well water was 89 to 213. Applications of complexometric titration, EDTA titration. First one is, estimation of metal ions in environmental sample. Accurately determines metals like calcium, magnesium, copper, zinc, nickel, lead, iron in soil and sediment. Second one is, food and dairy analysis. Determination of calcium and magnesium in milk, cheese, yogurt, fruits and vegetables. Third one is, metallurgy and mining. Determines metal content in ores and alloys. Fourth one is, industrial applications, used in industries where metal ion concentration affects product quality, soap and detergent industry, checking hardness. Thus, in summary, the understanding the principles, methodology, and theories behind color changes of indicators in precipitation and complexometric titrations helps students accurately identify endpoints and interpret reactions. Understanding the indicator behavior strengthens analytical skills, improves titration precision, and builds a strong foundation for advanced chemical analysis and research applications. Thank you for watching the Analytical Chemistry Vision. And if you've not seen Part 1 and Part 2 where you can learn criteria for volumetric analysis, how to prepare solution, expression of concentration, primary and secondary standard, and acid-base and redox titrations, and theory behind the color change of indicators. If you like this video, please visit our channel for more other interesting theoretical and experimental lectures. Don't forget to like, share, and subscribe, and share your feedback in the comments to help us improve further. Thank you.